Hello and welcome to this walkthrough for the OCR Gateway Physics, January 2012, Paper 1. In Section A of this paper, it's all about P1 and we're using these four equations at the top. Section A, Question 1. Phone masts send and receive microwave signals from mobile phones. Part A. Suggest whether or not having a mast near someone's house can be dangerous. Explain your answer. This question is worth 2 marks, so we need to make 2 very clear points. I've got a few here that you could make. First things first, people are concerned about that radiation can damage their health, and people are mostly concerned about cancer. The other thing is that the radiation from the mobile mast is high power, relatively high power compared to, for example, our mobile phones. And people will be exposed for radiation for long periods if it's in their home because they live there. So those are 3 clear points that you could make. You only need 2, but that's what I've put for this one. Then in part B, we have a similar style of question. It is difficult to make conclusions about the danger of microwaves to people using mobile phones. Suggest reasons why, and again it's worth 2 marks. So I've said, well, there's little evidence that long-wave radiation affects human cells. There is very little evidence out there. One of the reasons for that is because, of course, we haven't been using mobile phones for an incredibly long time, so maybe that evidence will occur in the future, but it's unlikely that long-wave radiation will be absorbed by cells. It's likely to be safe. Secondly, the fabric of the house would absorb some of the radiation. So we have there 2 clear points that show or explain why or suggest why conclusions about the danger of microwaves could be difficult to support. Okay, question 2. Bilha has high fuel bills. His house has poor insulation. Question A. Look at the diagram of a window in his house. So you've got basically a box here with the warm air inside the room clearly labelled, cold air outside, and of course the glass window. And so what we're going to have is we're going to have a movement of energy, thermal energy, going from hot to cold in that direction. A lot of energy is lost through the window. Explain in terms of particles, so we've got to use ideas of particles here, how the energy is transferred from the warm air inside the house to the cold air outside the house. And again, obviously, quality of written communication is important, and that means that basically you have to structure your answers. You have to structure them, use key terminology, and make sure they flow and are logical. So with the 6 marks in mind, I'm always looking for 3 kind of blocks of 2 marks, or maybe 2 blocks of 3 marks, okay? But here I think we've got 3 stages, 3 logical stages. We've got stage 1, where we're going to talk about how the heat is transferred from inside the house to the window. Stage 2 is how the energy is transferred through the window, and then stage 3 is how it's transferred to the outside. So what we have is we've got air inside the room, so we're clearly talking about convection, conduction, and convection again, because we've got air on the outside, which is the movement of air particles. So if all you did was identify those 3 processes, then you would be getting 3 marks out of 6. So this is my answer. It's a very full answer, but it will obviously cover probably more than the 6 marks, but it flows, it makes sense, it's logical, and it's a good example. So what I've started off by doing is saying that energy will be transferred from inside the room to the cold outside. Okay, it's an obvious statement, but it's a good opening statement. I then talked about convection inside the room. The warm air particles in the room are moving around quickly. A convection current is formed when warm air expands and becomes less dense, rising. The colder air then sinks, creating a convection current. Then I want to talk about how the energy is then transferred to and through the window. So when you have these air particles moving around the room, they're going to collide or hit the window, and they're going to transfer their energy to the glass particles, making them vibrate more. This energy is then passed to their neighbouring particles, and the energy moves through the glass by conduction. So obviously, classic conduction explanation about increasing vibrations being passed on to their neighbours. Then finally, of course, the energy travels through the glass. So then what you have on the outside is you have the cold air particles on the outside hitting the surface of the glass and gaining energy from the warm glass particles. They gain energy, speed up and spread out, and this causes convection and energy is carried away from the house. Part B. Bilha has two types of heater. They are filled with different liquids. Look at the diagrams of Bilha's heaters. So we've got two heaters here. They're identical in most ways, apart from one is filled with water and one is filled with oil. But apart from that, they both have the same mass, they both have the same starting temperatures, and they're both heated by the same type of heater. So heater 1 is filled with water, heater 2 is filled with oil. The water in heater 1 is at 20 degrees C. Bilha switches on heater 1, the electric heater heats the water. The heater supplies 2,100,000 joules of energy to the 12 kilograms of water. The specific heat capacity of water is 4,200 joules per kilogram degrees C. Calculate the maximum temperature of the water. So it's good old calculation. We're going to use the equation from page 2, which is that energy is equal to mass times specific heat capacity times the change in temperature. And it's important to realize that this is the change in temperature, as you shall see. We need to change the subject, so we cover over the T because we want to find out the temperature change. And of course that's equal to the energy divided by the mass times the specific heat capacity. So we have the energy here, which is the 2,100,000 joules. We've got the mass, which is 12 kilograms, and specific heat capacity. So carry out that calculation, you get an answer of 42 degrees C. Obviously that's the change in temperature. It started at 20, so we have to add that on to the 20 degrees. That gives us a maximum temperature of 62. So you get 2 marks for that part, and you get your 3rd mark for the last part. Part 2 of this question then asks, it is unlikely the water will get to this temperature, suggest why. So it's just that realization that some of the energy will be absorbed by the heater and the metal case and even dissipated to the surroundings. And of course, that's what I said in the second point, some of the energy will be lost to the surroundings. So this is only worth 1 mark, so either of those points would have got you that mark. Then part C, Bilha switches on heater 2. The specific heat capacity of oil is 1,670 joules per kilogram degrees C. The liquids in the 2 heaters are heated to a temperature of 50 degrees C. Look at the graph of the temperatures of the liquids in the heaters. So we have temperature versus time in minutes, and we can see the 2 graphs for oil and water, and quite clearly oil heats up quickly, water heats up much more slowly, hence the difference in their slopes, and that is because of their different specific heat capacities. Water-filled heaters are more useful for heating Bilha's house. Use the graph to explain why. So that's what we've got to do actually, is explain why. So the first thing I want to show is actually that I realise that this is to do with specific heat capacity. So water has a higher specific heat capacity, gets me 1 mark. What that means is from the graph, I can see that it heats up more slowly, but that will mean it will store more heat than can be transferred to the room. So the reason why water is more useful, because it has a higher specific heat capacity. Yes, it heats up more slowly, but what it means, it can store more heat, which will then can be transferred to the room, which is ultimately more useful. That's our 3 marks. Question 3. Sam puts a potato into her microwave oven. She heats the potato for 8 minutes. It is cooked through to the center. Sam also uses a convection oven to cook a potato of the same size. This method, using infrared radiation, takes more than 1 hour to cook potatoes through to the center. Sam's microwave oven cooks food differently and wastes less energy than her convection oven. Explain why. Now, this type of question, comparing infrared waves and microwaves in the way that they cook food, has come up a disproportionately large amount of times. Okay, so they do like this question. So the question is asking me to, it's talking about how that Sam's microwave oven cooks differently from her convection oven. So I'm going to come at this from the angle of the microwaves. I'm going to describe how they are different, okay? So microwaves are absorbed by water fat molecules. That's the first thing. And they do not directly heat the contents of the oven. In a normal oven, everything gets heated up. The trays, the tin that you put the food on, or the plate, or whatever, it all gets directly heated up, and that takes more energy, which is why microwaves are just initially being absorbed by the fat and water molecules, so it takes less energy because that's the bit that you're doing. You're just heating up those molecules directly, nothing else. So the second mark probably is for the fact that we're not directly heating the contents of the oven, because that links to the waste less energy. The other key thing is that they penetrate deeper, about 1 centimeter in the food. They cannot just say that the microwaves cook from the inside out and infrared waves cook from the outside in. It's too basic, because that's not strictly true, is it? If the certainly with a large item like a jacket potato, they will penetrate deeper, but not penetrating straight to the center, so you can't say it cooks from the inside out. So there is less potato to be heated to the center by conduction. So this is a good, reasonable observation. If you are penetrating deeper into the food, there obviously you'll be closer to the center, if you like. So the rest of the food is cooked by conduction or convection. And of course there's less distance for that to happen, so that's why it happens more quickly. Okay, question 4. Light waves carry information along optical fibers. How does light travel along the length of an optical fiber? Well, this is just recognizing that this is the process of total internal reflection. 1 mark. Information can also be carried along copper wires. Using optical fibers can be a better way to carry information. Suggest reasons why. So suggest some advantages of optical fibers. Well, we know that they can carry more information, or they have a higher capacity. We know that with optical fibers, information can be sent faster. Okay, and we know also that there's a less chance of interference with those signals, but also actually there's a chance that somebody can tap into your line and hack it, basically. But we only need 2 of those, so because it's only worth 2 marks. So part C asks, a laser produces a beam of light. How is a beam of light from a laser different from a beam of light from a torch? And to get 2 marks, you could just use 1 word here, and that word is coherent. Laser light is coherent, but what does that mean? It means it's single frequency, 1 color, and the waves are in phase. Okay, section B. Question 5. Amrit spends a lot of money on her electricity bills. One of her appliances is an iron. Amrit uses the iron for 0.5 hours and its power is 1500 watts. Electricity costs 18 pence per unit. Calculate the number of kilowatt hours used by the iron and how much this will cost. Okay, so the key thing about this is energy units are measured in kilowatt hours, which means our time must be in hours, which it is, and power must be in kilowatts, which it is not. So my very first thing I do is convert 1500 watts to kilowatts. So there's 1000 watts in a kilowatt, so we have here 1.5 kilowatts. I then use the equation from page 2, which says energy is equal to energy transferred equals power times time. So my power is 1.5 kilowatts, times it by the number of hours, which is 0.5, and we get 0.75 kilowatt hours. Then it's a simple matter of working out the cost. So every kilowatt hour costs 18p, so it's 0.75 times 18, which gives me a whopping cost of 13.5 pence. And so what we've probably got here is 2 marks for that calculation and 1 mark for that calculation. If you had used the 1500 watts as your power, you probably would have got the 1 mark for the first part of the calculation. So part B, Amrit has a fan heater has a power rating of 1955 watts and a voltage of 230 volts. The fuse in the plug states a maximum current of 13 amps. Amrit wants to find out whether the fuse is suitable. Calculate the current in the fan heater. So we want here the equation from page 2 that tells us power is equal to voltage times current, but we want to find the current in this particular one, so we need to change the subject. So from my triangle I can see that, change that to pen, see that current is equal to power divided by voltage. So here we have current is equal to power divided by voltage, which is 1955 divided by 230. So here we don't have to convert the power to kilowatts, it can stay in as watts, and that gives us a value for the current of 8.5 amps. So we have 2 marks there. Part C, Amrit decides to change to off-peak electricity. Off-peak electricity has advantages for producers and consumers. So, part 1, write down one advantage and one disadvantage of off-peak electricity for Amrit. So we're talking about the consumer. Well, obviously the clearest advantage would hopefully that there'd be less costs, that her bills would be lower, that it would be cheaper for her. But of course, putting things on in the middle of the night, like your washing machine and all that sort of thing, is inconvenient. And what it may mean is you may find that if you go onto that type of tariff, that actually your daytime electricity becomes more expensive to try and encourage you to do that. If you're very organized, that's fine, but if you're not too organized, then that may mean that you end up spending more money overall. But the key things are cheaper is an advantage, obviously, but it is inconvenient. And moving on to part 2, power stations produce electricity 24 hours a day. Producers sell off-peak electricity. This increases their profit. Explain how using more off-peak electricity can benefit energy supply. Well, the most obvious benefit is if you're encouraging people to use electricity at night, then you're evening out the demands, and you avoid those spikes in demand that can cause real pressure and loads on the national grid. So there are times when they can be very close to not having the energy that the country needs. And obviously it reduces waste, because if you're generating this electricity constantly at night and it's not being used, it's very difficult to store. So ultimately a lot of it is wasted. So anyway, you only need one of those points to get your mark. Question 6. Most scientists agree that the greenhouse effect causes global warming. However, other scientists disagree about the causes of global warming. So you've got 2 scientists here. One says the changes in the climate that we've seen are due to a natural cycle. Humans are not to blame. And then you've got the other scientist saying global warming is caused by humans. We've increased the amount of CO2 in the atmosphere. So part A goes on to suggest reasons why scientists may disagree on the causes of global warming. So suggest reasons. Okay. Right. Well, basically, there's evidence in the records that the Earth has gone through cycles of cooling and warming in the distant past. Okay, so maybe this current cycle is just a part of the natural process. There are also difficulties in collecting data on global temperatures. It's quite difficult to do, so that will lend some doubt to the argument. And then some scientists obviously have an economic interest in supporting or denying global warming. So not just denying, but also sometimes supporting. And what that means is they're working for companies or they're working for institutions where coming down on a certain side of the argument will provide some economic advantage, some money. Part B. Josh tries to explain what the greenhouse effect is. He says, methane and carbon dioxide are the main greenhouse gases. They trap heat below the atmosphere. It is something to do with the wavelengths of radiation, but I'm not sure what happens. So they want us to talk about here about the wavelengths of radiation, I'm pretty sure. So explain in more detail the role of radiation in the greenhouse effect and quality of written communication. 6 marker. So again, we're trying to look for those 6 points. Well, again, thinking about it logically, I can see the process where we've got explain how the energy gets from the sun through the atmosphere, how it's then absorbed by the Earth and re-emitted, and then how then it gets kind of blocked or trapped by the greenhouse gases. So what I've said is the hot sun emits short wavelength radiation that passes through the atmosphere of the Earth, and then that's absorbed by the Earth's surface, warming it up. Okay, so there's two remarks in there. The next thing is I then want to make clear that the Earth is then going to re-emit that radiation on a longer wavelength. So I've said the warm Earth emits infrared radiation with a longer wavelength. Some of this infrared radiation is absorbed by the greenhouse gases in the atmosphere. And of course, it's that absorption then within the atmosphere that traps the energy and warms the Earth. So I think that I've got my 6 points. I've covered most of the key ideas, but the key important thing is I've talked about this change in wavelength. And by the way, this is called the greenhouse effect. So it's pretty much exactly the same type of explanation you would use for passive solar heating. Very, very similar. Part B, the power station engineer thinks the power station could be made more energy efficient without increasing the electrical efficiency. Suggest how the efficiency of the power station could be increased other than by generating more electricity. So what we've got to do is we've got to reduce the amount of wasted energy. So if we talk about recycling the waste energy, you'll get 1 mark. But the important thing is to then state how it would actually be used. And you don't hear it too much these days, actually, but you would have some kind of combined heat and power scheme where that waste energy is used to heat homes and office buildings and factory buildings and all that sort of thing. And that gets you your 2 marks. That's the bit that gets you the 2 marks, is to state how it is used. Okay, I have to apologise for that because I didn't scroll up to look at the top of this question. So this is actually question 7 that we're doing at the moment. So I'll have to do the top part, and I've also got to own up to a terrible, obvious mistake. Okay, so let's have a look at it. I think it's a lesson worth learning. Electricity is generated in power stations from the energy stored in fuels. Fossil fuel power stations burn coal, oil or gas. Look at the energy diagram of a power station. So this question gives us a simple kind of like Sankey or energy diagram that shows us what the input energy is, and it shows us what the energy wasted as heat is and how much useful energy we're getting out as electricity. And that was the mistake that I did. I just did it too quickly and didn't read the question properly. Okay, so here we got calculate the efficiency of the power station. The efficiency is equal to the useful energy divided by the energy going into the system. So what I've done is I've used this wrong value here. It should of course be the useful energy, which is the 180 megajoules that we're getting out as electricity. So of course, if I put that into the equation, the answer is not 36%, it's actually 18% efficiency. The other thing I just want to mention is this idea of megajoules. Now, obviously, for most of our calculations about energy, we would convert to joules, but efficiency is all about ratios. So as long as all these numbers are in megajoules, it doesn't really matter. We don't need to convert to joules. We can just leave it as it is because it's a simple ratio. Anyway, if I had actually picked out 180 megajoules, I would have got 2 marks. On that particular question, I think I would have only got 1 mark because I used the wrong value. Question 8. Nuclear radiation can be both useful and dangerous. The 3 types of nuclear radiation are alpha, beta, and gamma. Look at the table about nuclear radiation. It is incomplete. Complete the table. So what we have in the first column, the 3 types of radiation. Then we have an example of their use and what they are stopped by. So, alpha particles, they are used in smoke detectors. Beta particles are used for measuring the thickness of paper, and they can be stopped by a thin sheet of aluminium. That's our 3 marks. 1, 2, 3. Part B, radioactive materials have to be disposed of safely. Some high-level nuclear waste from a power station is in liquid form. So it's high level and it's in liquid form. The nuclear power company want to bury the waste underground, the liquid waste underground. Explain the risks of doing this. Well, one of the big risks, of course, is that basically if you get a leak, then you can contaminate your local water supplies. And of course, what that will do is, obviously, if there is some kind of external contamination, it will increase the risk of cancer to animals and humans. Nice to see the animals getting mentioned there. There's your 2 marks. Okay, section C. Let's see if I can get through this section without making any mistakes. Question 9. Laura and Paul are learning about speed and distance in a science lesson. Paul walks around the school sports field. Laura calculates the speed at different parts of his walk. She draws a speed time graph. So let's just move that up a little bit. There we go. So what we have here is a speed time graph. So speed and obviously time. And speed time graphs are common on the higher tier paper because you can get 2 bits of information from a speed time graph. First things first, the gradient is telling you a little bit about the acceleration, because we've got a change in speed, so that's an acceleration. And then of course the other thing that you can work out from a speed time graph is how far the object has travelled by calculating the area under these sections. Okay, so if you work out the area of the section, whatever shape it is, a triangle or rectangle or combination of the 2, then you can work out how far the car or object has travelled. So in this particular example, Laura thinks that Paul accelerates in part A but decelerates in part C, then decelerates more rapidly in part D. So is she correct? Well, what we've got here is, we've got obviously in section A, we've got a positive gradient, which shows that she's accelerating, and in C and D we have negative gradients, which again shows that she's decelerating or slowing down, but there is a change in gradient, and the fact that D is steeper does mean that she's decelerating more rapidly in D, so she is correct. And then all we need to do is explain that. So all I've said is A has a positive slope showing acceleration, C and D have negative slopes showing deceleration, D has a steepest gradient showing higher deceleration. That's worth 2 marks, but we have to have all 3 points. So perhaps if you only identified the gradients as showing acceleration, deceleration, then you would only get one mark. So for part B, you might have to flick back to the graph to actually look at where I've got some of these numbers from. But the first part of part B asks us to calculate the distance travelled while Paul's speed is increasing. So that's obviously section A, because that's where you get a positive slope, positive gradient, and it's showing that the speed is changing and it's speeding up. And so I've just kind of sketched it here, but you need to look at that triangle in the graph, and what we want to do is work out the area of that triangle, and it's half times the base times the height. So using the axes, we can work out that the base has a size of 40 and the height has a size of 2.5. and half times 40 times 2.5 is actually 50 meters. So that's what we have to circle, 50 meters, and that gets us as 1 mark. Okay, so part 2 I think is straightforward, but they do like to throw just extra numbers at you to try and kind of like throw you off the scent a little bit. So it says here Paul walks a total distance of 540 meters around the field. Now that's actually an irrelevant piece of information, because it then goes on to say his average speed for the whole walk is 1.8 meters per second. He does a longer walk of 1.2 kilometers at the same average speed. So this is the data that we want to use. Calculate the time for his longer walk. Give your answer to 3 significant figures. Okay, so equations on page 2. Speed equals distance divided by time, but we want to change the subject to find the time, how long it takes. Okay, so that's distance then divided by speed. So time equals distance divided by speed. Now, 1.2 kilometers has got to be converted to meters. That's 1200 meters divided by 1.8 meters per second. That's his average speed. And that gives us 667 seconds to 3 significant figures. And there's our 2 marks. Question 10. A car manufacturer tests a car to find out its mean fuel consumption. 6 different drivers drove the car 700 meters in a test drive. The car was identical apart from the differences shown in the table. So this is quite a complex table with some information. So the trick about this is actually working out what information that they're giving you. So you've got six different drivers, same car, different drivers. That could be quite important. Next thing is that the car windows are either closed or open. Okay, and you can see here amongst the six drivers that some of them the car windows are closed and some are open. And then of course the other condition that they change is whether there's a roof box fitted on top of the car. And then you've got some data about the fuel consumption, which is in kilometers per litre. So it's how many kilometers these have traveled on 1 litre of fuel. Okay, so in other words, high numbers are good, low numbers are bad. Okay, high numbers good fuel consumption because you're getting very far on 1 litre, low numbers bad. And then, of course, you've got your CO2 emissions in grams per kilometre. So how many grams of CO2 are emitted per kilometre travelled. So I don't think there's much more. Let's have a look at what they say. So calculate the mean fuel consumption for the car from these results. Okay, that's straightforward. That's fairly easy. What we got to do is then work out then for the car, for all these different conditions, what's the mean average. You do this all the time. You add up the 6 numbers, as I've done here, and you divide by 6, and that gives you 15. So 15 kilometers per litre, that's the mean average based on all those different samples and tests. Moving down, it says, look at the fuel consumption data in the table. One of the test drivers produced a value well below the mean compared to the others. This is partly due to increased drag. Which driver is this? Choose from A, B, C, D, E, or F. So the identity of the driver was actually driver C. Let's go back and have a look at the data. So what we after one of the test drivers produced a value well below so we're looking at for the fuel consumption data. So the one that was well below is obviously the 12. You can see it's lower than all the others, and obviously, so that was C. So let's scroll back down. This is the problem with referring to a table. Identify what causes the increased drag and explain how this and other factors lead to the poor fuel consumption. Well, driver C, if you have a look in the table, the windows are open, and the roof box, obviously, that creates more drag generally. And what does that mean in terms of fuel consumption? Well, if you've got more drag, so let's just give myself a mark there, your engine's going to have to work harder to get up to those top speeds, and that's going to consume more fuel. And the other thing as well, okay, so you've got your physical differences, but obviously every driver is different, and you may find that the reason why the fuel consumption figures are so poor for driver C is that this driver may have been driving faster generally, or accelerating more, stopping, starting, or using accelerating much more around the circuit. So those are our 3 marks there. So 1, to recognise the effects on the drag. 2, to recognise that the engine has got to work harder, which means that there's an increase in fuel consumption. And then the third thing is to realise that also the driver's driving style could actually affect your fuel consumption. Question 11. Cars have many safety features such as crumple zones. Crumple zones help to protect the occupiers of a car if they're involved with the crash. Car manufacturers continually try to improve safety features for drivers and passengers. Explain in detail how crumple zones work. Describe how manufacturers test crumple zones, and then how they use their results to improve the future car design. So classic 6-mark question is given us 3 things to talk about, so you want to have a couple marks for each section. So let's scroll down and have a look at my answer. Okay, let's go back to pen, and here we go. So first thing I've said is I wanted first of all to describe or explain in detail how crumple zones work. So crumple zones are designed to reduce the rate of change of momentum on a passenger. So rate of change of momentum, just remember, is the same thing as force, basically. And I can, if I refer you to this equation down at the bottom here, we have your standard F equals ma. Force equals mass times acceleration. But if we substitute what acceleration is, which is a change in velocity over time, then what you have at the top here is you have momentum, because momentum equals m times v, and t on the bottom. And whenever you have t on the bottom, it's describing a rate of change, okay, per unit second or per time. And so what this says is that the rate of change of momentum is equivalent to the force. So if your rate of change of momentum is very quick over a short amount of time, the force is very large. If the length of time it takes for you to change your momentum is very big, then the force is very small. So what we want to do in safety features is we want to increase the amount of time it takes for the passengers inside the car to experience that change of momentum. And so going on, so they increase the time it takes for a passenger to stop in a collision. The longer the time, the smaller the force acting on the passenger. So I think we've described in detail there how crumple zones work. Then what we've got to do is we've got to move on to the next bit, which is describe how manufacturers test crumple zones. And it really is just common sense. This manufacturers can test crumple zones by measuring the forces acting on crash test dummies. They can then collect their data and analyze video from actual crash tests. And then finally, how do they use that information? Well, they will then use this data to redesign the crumple zone and then perform further tests with the new design features. So what I've done there is I've covered all three parts. There's 2 or 3 marks that are going to be wrapped up into this section, and then probably 2 marks here and 1 mark here. Okay. Question 12, and another large table of data for us to make sense of. Trevor wants to buy a new car. The salesperson at his local garage gives him a brochure with information about some cars. He looks at the information about the cars V, W, X, Y, and Z. Okay, so let's have a look at what the table is telling us. Engine size and capacity. So they're all got different sizes. Top speed in kilometers per hour. Time to accelerate from 0 to 90 kilometers in seconds. Okay, so these are all performance data. Now, this is often what becomes important for people these days, especially if you've got an environmental mind or you're concerned about the environment. Fuel consumption in kilometers per litre. So just like the previous question, kilometers per litre means that the higher the number, the better the fuel consumption. CO2 emissions in grams per kilometre. Okay, so the more CO2 emissions, the worse it is. And then finally, of course, noise level in decibels. So people like to have quiet cars, generally speaking. Okay, so Trevor wants to buy the car that is the most economical and does the least harm to the environment. So he wants a car that has the best fuel consumption and the lowest impact on the environment. He talks to the salesperson. Car X has the best fuel consumption and is quiet, and I like the performance figures for car V. Okay, so Trevor is saying that car X has the best fuel consumption and he likes the performance figures of car V, which are these basically. The top speed, he likes the fact that he goes at 201 kilometers per hour and that he can do 0 to 90 in 5 seconds. Okay. And then the salesperson says, I don't think either car is the best one for you. You're misinterpreting some of the information. I would suggest car blank. So remember what Trevor wants. He wants the car that was the most economical and does the least harm to the environment. Okay, so he needs to rethink his ideas. So scrolling down, the question asks, explain how Trevor has misinterpreted the information and suggests with reasons which car he should buy to meet his requirements. So his requirements are low fuel consumption and good impact on the environment. So the key thing here is when he was looking at the fuel consumption figures, he just got them the wrong way around. He obviously assumed lower the number was better, but obviously that's not true. It's how many kilometers you can do on a litre of fuel. So he just got that mixed up. So that's the first point we've got to say, is he just got the decision the wrong way around, the number the wrong way around. And then, so in terms of then understanding what that means, then if you have a look at the table, car Z has the best fuel consumption data, and therefore it would have the lowest costs in terms of running the car. And then his second criteria was the environment, which is basically noise and CO2. And the car that has the best environmental performance is car Y, because it gives out the least noise and it has the best CO2 emissions, in other words, the lowest CO2 emissions. So there's our 3 points. Part B, Part 1. Trevor test drives one of the cars. It has a weight of 12,000 newtons. He drives with a net driving force of 500 newtons for a distance of 850 meters during part of the drive. This produces the maximum engine power and takes a time of 35 seconds. Calculate the power. So hold on, 35 seconds, and we've got to calculate the power. Right, power is basically equal to the energy transferred per time. So it's a rate of energy transfer. But remember in physics that energy transfer is, in mechanical terms, is the work done. Okay, so here what we're going to do is we're going to combine two equations from page 2, the power equation and the work done equation. So work done, so power would be equal to the energy transferred or work done divided by the time. Now remember, work done is force times distance, so it's going to be force times distance divided by time. And you notice up here that they gave you the weight of the car and the net driving force. Okay, so the key thing about work done is that the force that you're interested in is the one that's acting in the line of the distance traveled. Okay, so in other words, we're not interested in the weight here, we're interested in the driving force. So we've got 500 newtons times 850 meters, which is distance, divided by 35 seconds. Put that into your calculator and you'll get 12,143 watts. And of course in kilowatts, that's 12 kilowatts. And there's our 2 marks. Part 2 then says this represents the highest power of all the 5 cars. Use the information in the table to explain which car Trevor has driven or drove. Assume the mass of each car increases with engine size. Okay, so basically V, if you look in the table, has got the largest engine. Now the bigger the engine, the more powerful it is. So this car must be car V because it has the largest engine, and on top of that it has the highest top speed and the highest acceleration. So it's car V because it has the most powerful engine, the largest engine. Part C, Trevor's friend John lives in the centre of a city. John is considering buying an electric vehicle to drive on the inner city roads. Look at the 2 examples of electric vehicles. And the only thing here that's of interest, that's relevant to the question, is that it says here in the middle, batteries need recharging. Okay, so electric powered vehicles could increasingly replace petrol driven ones. That is true. Discuss the implications for drivers and pedestrians if this happens. Okay, so what will happen? What will be the implications if we do replace all our fossil fuel powered cars with electric vehicles? Well, the first thing is there would have to be, we'd have to put in the infrastructure to support electric cars. It's just not there at the moment. So there would need to be more charging points for electric cars. They will have a limited range. So there are lots of points you could mention here. There are a lot of things, but the key thing is the thing that limits electric car technology at the moment is this lack of infrastructure, this lack of charging. Also, so in terms of the so that's for the drivers. So in terms of the pedestrians, electric cars on the road would mean that it's much quieter. Now that has 2 major impacts. The first impact is obviously, until we certainly get used to it, it could increase the risk of injury through accidents, just because we do rely on all our senses. And I know I've done it. I've crossed a road and very often I'm listening as much as looking. So the fact that they're making less noise, that they're quiet, could mean that we're more likely to have a car accident or be hit by a car. But that's a negative thing. I guess the positive spin on that is actually overall, especially if you live next to a noisy road, that there'd be less noise pollution, which would be a good thing. Okay, we're near the end now. Question 13, last question. Molly is investigating falling objects in a science lesson. She drops a piece of thin card from the top of a staircase and measures the time it takes to fall to the floor. She then changes its shape and repeats the test. So I need to scroll down a little bit here. So there's not much on the diagram that I need to pay attention to, I don't think. So look at Molly's results. So we have the 3 samples of card. Well, it's the same piece of card actually, but the shapes, 3 shapes that she makes with the card. And these are the results. So the card sheet initially has a cross-sectional area, or an area of 1200 square centimeters. She then folds it in half, so that reduces the area exposed to the air to 600 square centimeters, and then finally she crushes it into a ball, and that reduces the area to 150 square centimeters. Key thing here is because she's using the same piece of card, the mass is constant, and of course, unsurprisingly, the time it takes to fall to the floor decreases as the surface area decreases. Okay, so what do we have to do? We have to put a tick in the box beside each correct statement. So some of these statements are incorrect. So let's have a look at the first one. All sheets of paper have the same drag force while accelerating. But that's not true, because you're changing the surface area, therefore you're changing the air resistance and the drag force. The weight of each sheet is equal to the drag force when they fall at terminal speed. Well, that is true. So at terminal speed, you have the drag force equaling or balancing the weight acting down, which is why you reach that constant velocity. So that's true. The time to fall is directly proportional to the exposed area. Well, that would mean, if you directly proportional would mean that if you doubled the exposed area, the time it would take to fall would also double. And if you look at the results, that's not true. Then this one, that the drag on A is bigger than the drag on B, which is bigger than the drag on C when falling. Well, that is true because the surface area is getting smaller, so the drag forces are getting smaller as you go from A to B to C, so that's true. And then at terminal speed, the loss of GPE increases the thermal energy of the surrounding air particles. Well, that's an interesting one. So yes, that is true. And the reason is because if you just imagine this, what's happening when an object is falling and accelerating is you're getting a transfer of energy from GPE, gravitational potential energy, to kinetic energy. Okay, but when you get to that point where the terminal velocity, where the object is not getting any faster, but it's still losing, or it's still shifting gravitational potential energy, where's that energy going? It's not going into the speed of the object. It's not increasing its kinetic energy anymore. So where can it be going? Well, the only place it can be going is it's been dissipated to the surroundings. So that last bit is true. And that brings us, hopefully, I think, to the end of this paper. Yes. So well done. Keep going. I hope you found this useful.